never mind. The course website, kind of confusing. We have several options or several ways to get confused with this, and that's why I will tell you what it is. The Google Doc is where most of the content is going, linked to PDFs of the lectures, timetable, when homeworks are due. Everything that happens on the Google Doc. You will, so D2L you'll use to get to the recording, unless you're using Twitch. You have Pinapto that you can reach from D2L. That's roughly what we'll do. Gradescope is your submission of homeworks, your answer of the homeworks is all done via Gradescope, and discussion in course are done via Piazza. So it's like the good of everything. To read the homework, you'll use Overleaf, so open an Overleaf account. You don't have to, but Overleaf is a GUI that gives you way to read LaTeX documents. Docs in Overleaf. And if you want to submit your homeworks, it's not mandatory, but if you want to use LaTeX to submit your homeworks, you can use Overleaf as well. Basically, I'm giving you a template of the homework with the questions, and you can add to the LaTeX document your answer, or you can add it in text or in figure, or to write piece of it in your handwriting and add it as a figure into the LaTeX document. Any of the above is fine. You can submit it completely. What I need from the homework once you submit it is a PDF that is very readable. If it's handwritten or figure or some combination of the above, it's entirely up to you, but it has to be readable. So yes, open an account in Overleaf. Because at least I will publish the homework by giving you an Overleaf link to read it. The reason is that if there are then questions, clarification, and I can want to change it online instead of spamming your email with, hey, I added the comma over there, I'm just changing. If there is nothing crucial, I'm just changing the PDF. And to get to the PDF, as I said, use Overleaf. Okay.
So do we submit homework on LaTeX or Gradescope?
You can submit, or no, you will. The question is, how do you create the homework? You submit it on Gradescope. Gradescope wants PDF. Gradescope wants PDF. How do you create a PDF? I like LaTeX, I'll suggest LaTeX. Gotcha. You want to have LaTeX, but you don't want to worry with exact figure, you just want to do handwritten figure and then take a picture with your cell phone and add it as a snapshot. You can do it with LaTeX. You want to create your homework all by handwritten or all with, God forbid, Microsoft Word, be my guess. Just submit PDF. Okay. Once the homework is published, here is an algorithm that I recommend to all of you online, and I'll mention in a moment more about online, but for people here, read the question carefully for the homework. If you need it, rewatch my lecture. Some of the material has been taught to death by many other lecturers, much better than me. Watch the lectures of my lecture again. If you need, think really hard, try to come up with ideas that do work, ideas that don't work. And after that, you are welcome to meet with your peers. Other students, if you're here, other students online in Piazza. There is a way to find to ask for a partner to work with. Piazza gives you a way to, I will not get into it, but Piazza gives you a way to meet electronically people to work with. All good. Meet with them. You can discuss in high level your solution. And this is a very thin ice that I'm talking about here. Right here about what is cheating and what is not. If you're discussing with your peers, your high level and your own ideas, not what you find on Stack Overleaf, not what you found on other sources on the web, not what you find in check.com, lot of other resources to find solutions, but if you have some ideas, you're meeting with your peers and discussing the high level ideas, it is not cheating, quite the contrary. I'm encouraging this type of brainstorming together. Okay, what you're not allowed to do is to replace any written material. Don't give the solution to copy and paste for anybody else. Then go home and write the solution all by yourself, from your own memory. Everything that is divergence from it is an cheating. Okay, and I'll do my best that it will backfire for you during the midterm and the final. That is, I'll try to, if I'm asking in the midterm a question that is similar to a question that I ask in the homework, and I expect everybody that solves the question by herself, himself, to be able to answer this question, and you are doing poorly in this question, I'll have to assume that you did not answer it in the homework, even if you submitted, which is, so the grading is much more severe than the grading of just you didn't know the answer. Okay, so make sure that you understand everything, make sure that you know how to write the solution by yourself, and so on. Okay, so as I said, collaboration in the level of brainstorming, fantastic. Small group only, fantastic. If you get the idea from somebody else of your solution, it's fine. But please show the courtesy of saying, I got a solution from John Smith. It's fine. It's a legit behavior. I tried, I thought that I know what the solution. John Smith explained that this is not a good idea and suggested something else. That's great. Just, you can, if you are nice and give and respectful, say this is a solution that we got in teamwork and I was working with, write the name of your solution, of the partners that you use. Okay, and sharing text is of course cheating, as opposed to sharing ideas. Sharing text is cheating, which starts to be a thin line if you're discussing it electronically. So Zoom is fine. You know, use your judgment. I have a funny grade scheme, final grade calculation that I'm using that essentially checks the Google document to tell you exactly how grades are split, but I'm looking at the midterm, I'm looking at the final, looking at which one has a higher grade and give 12 more points to the one that is higher. Why? If you did poorly during the semester, you caught up towards the end of the semester, you're doing great, very good, you get more grades. It's almost as a second chance, but the lower grade still plays a role. That being said, if you did great in the midterm and you feel that all I need is a B in the course, so I will not even try the final. There are a set of rules, again, in the Google document that says that you have to get a minimum grade in your final. If you are doing really poorly in the final, it might cause you to fail the course, no matter what is your average grade altogether. Get 30 out of 100 in the final exam, and good chance that you'll fail the course, even though all your homeworks and your midterm is fantastic. Let's make it clear, and the exact formulas are in the Google Doc. Okay. Video recording, we said you'll have it on D2L, you'll have it on probably on Twitch. Each one has its advantages. You can survive the course even if you didn't take 345, but you know a lot about data structures from other sources. You'll probably do fine in the course. You can survive the course, but you have to be very careful about not assuming that you know something even about common notations that might be confusing. So if you took 345 and you did great in 345, fantastic. Piazza, all the discussions, answering of clarification happens in Piazza. That's why I want you all to be on it. Various bureaucratic, what is exactly the material for the midterm, it's all on Piazza. You are in another fine line that almost every semester that I'm teaching, 445, we got into problems on it, is what type of questions are not legit to ask. Piazza doesn't give me a way to censor the question before you post it. If you're posting a question that suggests anything about what you think, correctly or incorrectly, but what you think is the way to solve the question. Can I use Quicksort to solve homework 3, question 7? And you can specify when you're posting in Piazza if this question is visible to everybody or visible only to the staff. If you have any doubt, make it visible to the staff only, Amir and myself. If you're posting something to the whole question, maybe you're frustrated, maybe it's late at night, you didn't notice, and you're suggesting something about how to solve what do you think is possible way to solve this question, it's cheating. Don't do it. Okay, to start with, I'll take you off Piazza. After that, maybe I'll use other things because it's violation of the code of conduct. Don't hint to other students what is, to the whole class, what do you think are possible ways to solve any questions? Okay, clarification questions are fine, something that hints about ways to solve the question are not fine. That being said, I do want you to be very active in class participation, both here or on Piazza. Be active, I'll give you credit, I'll give bonus questions, I'll generate discussions. If you want recommendation letters, you want to improve your chance for higher grades, shows class participation. Improve my opinion about you, make yourself visible to me by doing some extra work, getting some, being particularly active. I like it, it's something that I'm using for recommendation letter, it's something that can make you move from A to B and so on. If you look at the formula, if you're getting 90 and up, you'll get an A, most likely. Again, modulo what you're doing in the final exam, but most likely, if your overall numeric grade is decent and is more than 90, I think always an A is guaranteed. If you're getting 80 and up, modulo the final exam, B is guaranteed, but possibly an A if you get 87. Will it be, if you got 89, will it be an A or an B? At this point, I'm looking at all your homeworks, I'm looking at class participation, anything that can give me more hints about how did you do in the class personally, and that will help me decide if it's an A or an B. Similarly for C and D, similarly, and so on. Okay, so that in general, of course, 80 and up is at least a B, 70 and up is at least an C, and so on. But once again, be careful with the final exam. Don't not attend to the final one. Okay, attendance, well, as far as as remote classes participate is concerned, recommended active learning. I don't know if we'll be able to do it when it's distance learning. We'll do our best. Okay. Some of you took the course with Stefan last semester with Professor Koborov. Materials are related, similar, but not identical. Okay, fair warning. Professor Koborov and myself are teaching the course in. Each one has his own point of emphasis that we think are really important and are not necessarily identical. So don't assume that because you almost pass Professor Koborov's exam, then it's going to be, you don't need to, there will not be any new material. There are definitely different things in the way we are teaching algorithms. Textbook, you don't have to have any textbook. Frankly, the slides, I think I'm using them for the last 20. Some of them are going and from times that I was TA even. And going back many years, slides are good. You can do with mostly the slides. CLRS, not my best, it's pretty high on my list. It will not be my top recommendation. Book, sometimes it's getting a bit overly complicated to my taste. Still, it's a textbook that everybody has or very cheap to get. Recommended. It's and in some parts like hashing, we will use a lot of. The course will be quite similar, or even using the slides from CLRS, Common License Software with Stenstad. Best textbook that I can recommend is the one by John Kleinberg and Eva Tardosh. Fantastic textbook, but expensive. Okay, I'll take a few examples here and there from this textbook, and I'll tell you when, especially in dynamic programming, they present it in a really, really beautiful way for dynamic programming. If you can afford this textbook, great. Again, not necessary. That's a very cute textbook by Desgupta et al. I think even available online. And I also recommend go to Amazon. There is a fantastic textbook about data structure. Skip list, I'm teaching from here. Some parts of hashing, some part of, and this textbook is, for whichever reason, went out of fashion and is dirt cheap, especially if you're going for used one. I have a few copies that I bought for, I think, like $7 each. Go order it, having it on your, having it in Europe, by Louis and Dannenberg. It's not for the whole material of the course, only for the data structure parts, but the material that it does teach, it's doing fantastic job. People, any questions so far? Okay, let's start with grading. I don't remember if I missed this slide. We will have 6 or 7 homeworks, more like 7. You have to answer 6 of them. If you're answering all 7, you're getting some bonus points about my personal appreciation for you. That is, let's say that you did poorly on homework 3, but you still survived somehow to get your target grade without homework 7, even though homework 3 is so low. Doesn't mean that you care less about the course, so I feel less inclined to, again, if you're getting to the gray level between A and B, not submitting homework 6 despite being able to improve your average, but you didn't take this opportunity, I'll think about it as you care less for the course. It's not a bad thing, but it's not something that I'll use as a, that's why I'm promoting you from B2A. Okay, we are going to discuss a lot of problems from algorithms. I could have picked many other sets of questions from algorithms, obviously, and so many topics. Why are these algorithms? Why do I use big O to measure complexity? I'll talk today, at least a big part, about models of estimating complexity of algorithms. And I'm well aware that it's at most refreshing. For a lot of you, you've seen big O before. You know some analysis of running time of algorithms before. Nevertheless, I'll show a few examples that I think that are originally mine. And please make sure that you walk through the examples, even if you do know you have seen big O in at least in 245 and 345, many other courses, high school. Everybody uses. So we are using the big O notation. I'll mention it formally in a moment. Big O of what? Sometimes of basic operations like CPU, single processing CPU in this case. How many basic elements of the CPU are we doing? But in other algorithms, we will use big O to actually say the bottleneck of this algorithm is not the CPU operation. The bottleneck of a lot of dynamic programming algorithms is that you need very large tables, enormously large tables. What happened to your memory when you are using enormously large tables? For a while, your memory says, fine, I have 1 gig, 8 gig of memory, I can stick it all inside my main memory. And what happens then when you're asking for a 10 gig array? The memory still says, I'll pretend that you have all of it. The cache will say, I'll pretend that you still have all of it, but actually it will start to do paging, moving pieces back and forth from slower memory. Maybe hard drive, maybe SSD drive, either way. It will be much, much, much slower than everything at once when you have a small memory. And sometimes the memory requirement will be so ridiculous that with your SSD attached, hardware attached, you will still, the space will be the bottleneck, not immediately the running time. So again, large memory of the algorithm might be just by itself renders the algorithm impractical, or sometimes it might require caching, moving things between the slow and fast memory, which will make the algorithm much, much slower than what you thought it would be. Either way, space in many cases is much more important than memory. Sometimes we will talk about I/O efficiency. We will talk about B trees. For example. And B trees are search trees. They're probably the most popular data structure out there. All databases using them. They have geometric relatives called R trees that are more for geometric object. B trees are just for keys like family name, IDs, anything that is single parameters. And these are not the most efficient data structure for most cases that you can find if you want to help. Let's start from the 3 common operation of find key or insert of a key or delete. This will be 3 major operations that we'll see coming again and again. And sometimes we'll want to ask operation like count of between K1 and K2. I will ask you how many keys are there, how many people are there that makes between 70 and 80 K a year, or how many people are there between this height and this height, or any type of range queries that I want to do. So B trees and R trees will be able to support all these operations efficiently, yes. Are they optimal? Depending how you set the parameters, mostly not. Most cases they are not optimal. So why are we using them nevertheless? Because I need to actually look closer about optimal for what. Are they optimal in terms of CPU usage? Probably not. Not when you measure the CPU. But what determines the running time of your algorithm in many cases is how many times you are going to your slower memory, hard drive, SSD, network, cloud. How many times do I ask the cloud or the SSD to send me a piece of data or to push a piece of data back to the memory? That I'm counting how many IOs operation, read and write operation, I have to do. And in many, many practical cases, the number of IOs, the number of read and write operations that I have to do is much more critical than how much CPU operations I have to do. Okay, and that plays much more important role about determines how fast or slow your algorithm is. Especially if you have a hard drive disk where each read and write was really slow because you had to move the head of the hard drive. You have to wait until the correct track of the hard drive will reach. It was very slow operation. So the number, but it's also true for SSD. It's also true for, of course, the cloud. Number of IOs is a much more important bottleneck than the number of CPU. CPU runs fast as a rule. Memory, especially if you don't have it in your main cache, will be the bottleneck to the performances. So we'll care much more about I/O in certain cases. And for I/O operations, B trees and R trees are doing fantastic, which explain why they are one of the reasons they are so popular. Okay, so we'll ask what is the complexity of the algorithm, but what is the complexity? Not necessarily about CPU operation, but maybe about the space complexity, maybe about the I/O efficiency, how many read and write, again, that's a big O. Sometimes I'll ask about parallel steps. Let's say in this algorithm, but if I want to use a parallel computer, want to use CUDA, want to run it on the cloud, I'll ask how many parallel steps we have. Not sure that we'll touch upon it in this course, but need to know it's important. That, for example, if you want to sort a lot of elements, then you need at least log n parallel steps, meaning you have n keys to sort. This is kind of less, but if I have n keys that I need to sort, and I have a parallel computer, let's see. Come on, I can take two keys and compare them and say, hey, if this is larger than this, and maybe I'll switch the order, and this I'll do with one processor. And here I'll have another one with another processor, and another one with another processor. And do it for all the keys in parallel. This is one parallel step. And to sort them all together, I will need, I'm skipping the details, don't expect to know how to do it, but I'll need altogether at least log n many parallel steps every time that I want to sort any n keys. No matter how many processors, how large my computer is, there are bounds on how fast can I sort. related to parallel steps, but not the same. GPU is used, as you all know, to many more applications that are not related to the graphic of the GPU. There are many algorithms that run extremely fast because GPUs are implemented so efficiently and provide a lot of parallelism in the GPU itself. A lot of pixels or a lot of processors, each one with its own issues, but they are all working in parallel, kind of, as each pixel on your screen working in the GPU, but GPU has a lot of other constraints that parallel computers don't have, like dividing into threads, what type of access to the memory you have, and so on. So analyze the complexity of an algorithm that is implemented on GPU is important and is a headache.
So in that diagram, like, are you saying that like each of those can be processed by separate processors? Like as a processor is comparing the first one,
I mostly refer to CLRS, the part about sorting networks in CLRS, but roughly it's I can generate a parallel sorting algorithm I can implement it via my CPU, obviously, even though it's parallel, I'll just ask my CPU to pretend that it's different processors. Or I can ask a bunch of processors to work together. And a natural way to ask from each processor to work together is look at two keys and maybe replace the order. Maybe you don't need to replace the order. And if you build it for enough many steps and adding a lot of detail that I'm skipping, you'll see that even if all the processors are happy to work together, then you have another set of processors, maybe it's the same processors, different, that will work in the next level, another set of processors. But if it takes at least a second for a processor to work, to make its decision, no matter how many processors I'll have, then in most reasonable models, you'll need at least log n many levels of this network, at least log n seconds, even if you have a lot of processors. But that's with some assumption of the inputs, that is, because there are types of inputs that you can sort very fast. There are types of inputs that you can sort on single processor in linear time. Okay, first question. When can I sort a set of keys in linear time? Okay. It's a question of have you studied it in previous courses or not? Do you know about sorting algorithms that can run in linear time?
I was just thinking about the input. Like if the input is in reverse, you could
If the input is?
in reverse. So like if the larger number is at the start, the small one is
Excellent point. So for all the algorithms, for every algorithm that we'll discuss, there is always a very friendly input that will cause the algorithm to run in less. For example, if I'm asking you to sort elements, and the first thing that your algorithm does is, hey, check if they are already sorted, or maybe sorted in reverse order, and if it does, then I have to do very little, then I don't need to worry about it. We have a slide saying that usually we are worried about the worst case running time. That is, if I'll give your algorithm the worst, I'm the mean vicious adversary, and I'm trying to feed your algorithm with the one that will cause it to run in the slowest time. Either an algorithm that no matter how vicious I am, it will still run in linear time. Have you heard about it? If not, we'll talk about it. What?
Is quicksort one of them?
Quicksort is not one of them. Quicksort is not even the quickest asymptotically sorting algorithm, but it is in practice.
Wasn't some version of like radix sort?
Radix sort will do. Radix sort is built based on bucket sort that says I'll take a key, and based on this key, I'll put it in this bucket, or this bucket, and this bucket. And then on top of it, radix sort, we can talk about radix sort in this big. about it in the course. Definitely one of my favorite, unbelievably brilliant to my taste, completely counterintuitive. Radix sort is great, but it requires the keys to be very well structured. It will not work well for rational numbers. It will not work well for floating points. It will work well if the numbers are integers and they only have a few digits when you represent them in base 10. Then radix sort will do great, but it only wants very structured, very limited types of inputs. Okay, so one common thing about algorithms that we'll discuss in this course are discussion about complexity. I'll also discuss paradigms of the algorithm, like subclasses of the algorithm that says, I'm using this algorithm, use divide and conquer. I'll take the input, split it into two pieces, solve each piece recursively, and then merge them. Quicksort is such an example. It takes the input, it splits it into small keys and large keys, sort each one recursively, and then puts them together. Merge sort is another divide and conquer algorithm. It takes the input, sort one half, sort another half, and then do merging of the two pieces. They are not necessarily small and large, which makes it, but it's another example of divide and conquer. That's one of the paradigms. And we'll see a few other paradigms, quite a few other ones. Such paradigms might be greedy algorithm. At each iteration, I'll do the steps that gives me, in the short run, the most benefit. Each step, I'll find the next element that gives me the best benefit. And greedy algorithms will be algorithms that use this paradigm, and sometimes this paradigm will actually yield global optimality. Even though I don't care about global optimum at each step, I just care about who is the next element to add that gives me the most revenue. Greedy algorithms will still give great solution. Good example for it are, if you want to, I don't know if we'll talk about it yet, but if you want to look at Hoffman codes, you don't need any coding or any information theory to understand how Hoffman codes are. It's one of the best algorithms in terms of compression ratio. If you're a fan of the TV series, the Silicon Valley, there is a fair amount of references to Hoffman code. It's a very, very simple algorithm, and yet gives you fantastic compression ratio. So that's a case where greedy is doing very well. And we'll see other algorithms that really are doing great. Divide and conquer, mentioned it, for example. Merge sort, quick sort, good example. Dynamic programming, another paradigm that we'll use. We'll use a lot of dynamic programming in the course, and as we'll see, in dynamic programming, we'll see how to find the largest common subsequences. We'll see what is the maximum similarity between two files, and how do I find, if both of us worked on the same file last night, but you did some changes and I see some changes, how do I find what of the file remains the same and which changes each one of us did? What you know as a diff command in editors or in Unix between files, what's common. That's examples of dynamic programming. We'll also see what is the most likely word. We'll see if I I went to my keyboard and I typed the word. Went to my keyboard and I typed the word hello. And my editor thought about it a bit, and it will wonder, this is not a word in the English dictionary. So what maybe did I meant when I wrote this word? Maybe I meant to write the word hey, maybe I meant to write nice, or maybe I meant to write hello properly. Which of these three options I probably meant to write if this is what I typed? And what my editor will do, to some extent, is to ask if the word that you mentioned was, hey, what types of errors happens in the process between you thinking conceptually about the word hey, but you typed hello? It means the H might stay the H and the E might stay the E, but all these different letters, instead of typing Y, I typed LLOW. I had a long series of errors that caused me to type this word while this is what I had in mind. How many errors happened on the way from here to here? And you'll see that here the number of errors is about 4 errors, 4 typing errors. If you think about each letter that I misspelled, then here are 4 letters that I misspelled. I'll ask, maybe I meant to write nice, but in nice it's even more errors because none of the words, the letters here is the same, so the number of errors is actually, instead of each one of these, I type one of these, so this will be at least about 7 errors, depending how exactly you count. While if you think about the word hello, then it's only a single error. So in a sense, that is most likely that will be, in a sense, the most likely explanation to what I actually typed. Make sense? So that will be a reasonable, correct suggestion of the correction of what I actually wrote. And maybe that will be the suggestion of what the editor will suggest of. Maybe that's what you meant to say, because that's the nearest word to what you actually typed. Again, that's the nearest word in some sense to what you actually typed. The most logical, most simple explanation. And we'll see how similar ideas are used to find similarity between sequences, between DNA sequences, between images, between curves, by measuring distances, and we'll all do it using these dynamic programming approaches. And oh, by the way, you know how to, of course, we'll talk about it, I don't know for how long, but we'll talk about finding distances in graph. What is the shortest path from some source to some destination? What is the shortest path in a graph between a source to any destination? What is the shortest path if every edge costs just one hop, one unit? Then we can use BFS. What is the distance if every edge has a cost but it's positive? Then you can use Dijkstra. What is the cost if you have negative and positive, or a few criteria? Then we need more complicated algorithms. All these algorithms also falls under dynamic programming approaches, one of the most useful parameters. I'll try to pick algorithms that are relevant to many areas. And I'll also try to pick algorithms that I think, or tools. We'll talk about ILP, integer linear programming. And this I'm giving you because I think that for the money that you are paying, talking about linear programming and integer linear programming, expose you to tools that there is the highest chance that you'll use later in your life, either as researcher, as programmers, software engineering. Later on, linear programming and integer linear programming are like big hammers that many problems that you might face can be solved with these tools. That's why I'll pick these algorithms. Another criteria that helps me to phrase this course, decide about what we're studying, is of course, not less important, the coolness factor. If I hate something and I find it boring, maybe I will not teach it, maybe I'll teach it less. There is just this much of dishonesty that I can show. There is enough many great, useful, extremely cool, brilliant things to teach you rather than wasting your time on things that are less cool, will not teach you new ideas. My approach of sitting here and wasting your summer is to at least trying to give you tools that will be useful for you in some way in the future. And there is enough many cool things that I can pick in this approach. Okay. Knowing when running time counts, I wanted to have this sentence just to say I'm not obsessed about running time always. In many cases, in many real problems, you are just implementing something, and for the problems that you have in mind, whatever you do, even though it's not the most efficient algorithm, not nearly the most efficient, you're doing exponential search and all the bad things, and for the problems that you actually have to solve, it's just fine. Let's talk about it. Let's try to set the rules about when should you care at all about running time, and when should you say, hey, my problem is small enough that my time as a programmer is much more efficient than the running time of my computer. I'm not going to waste my time on improving things that I don't need. And I wanted to mention another point that separates to some extent instructors of algorithms or researchers of algorithms, which is how do we treat randomness. So let's talk a bit about randomness. So when I'm telling about an algorithm that is randomized algorithm, what I'm trying to say is that at some point the algorithm needs to say, I'm taking this decision or I'm taking this decision. I looked at the data and I'm doing this or I'm doing this. And in randomized algorithm, sometimes the algorithm will say, you know what, I'm not sure, so I'll toss a coin. I'll call the random generator, and based on the values that I'll get, I'll make my decisions. Sometimes without looking at the data, sometimes with looking at the data, but with random data. That is, the algorithm is not deterministic. We have deterministic algorithm. Deterministic algorithm means you'll take the same input and you'll run the algorithm again. The algorithm not only will give the same output, but every step will be completely identical. Randomized algorithm, you might run it again, but get different results. Because the algorithm took the liberty to do things in a random way. And guess what? I'll try to convince you that randomized algorithms in many cases are much more efficient. Easier to program, give you better results, almost always. And they beat, in many cases, the deterministic algorithm. Even though there might be some slim chance that they will not do what you want them to do, or at least not in the speed that you want them to do. And you'll see quite a few examples in this course that doing random decisions actually helps. Do you guys have ideas of when did you use randomness? Where did you see randomness? Yeah.
Picking the pivot in Quicksilver.
how do you pick a pivot in quicksort? So let's mention quicksort. So what generally happens in quicksort, and we'll talk about it much more, but when in quicksort, and I'm just giving you the highlight because we will revisit it more clearly, we'll pick a pivot X as a pivot, some number, and then we'll arrange the elements in the array so that by moving elements from the left side to the right side, until in the left side I'll just have elements which are smaller or equal than X, and in the right side I just have elements that are strictly larger than X. That's the idea of quicksort. So once I pick the pivot, I need to split the array into two pieces, small elements and larger elements. This is A. And next, I'll just take the small elements and do the same operation recursively, and the same for the large elements until I'm just left with arrays of just single element in each one. That's roughly how quicksort works. And then depending on who taught you 345 or whenever you saw quicksort the first time, there are different strategies of how do you pick the pivot. Some people, including the textbook, including CLRS, will start by, let's take the first element, let's take A1 as a pivot, the first element, or A0, whichever. So, that will be my pivot. Is a good strategy? In practice, probably yes, depending on who provides the input for you, but it's quite likely be that in practice it's doing not too bad. Other people will tell you X should be the median. Pick X as a median of the array. With a median, elements such that you have about n½ keys which are smaller than X, and n½ keys which are larger than X. So it's a different strategy. Will it work well? Well, if you know who is the median, then it will work fantastically. The algorithm will run in the optimal time, which is n log n. Why n log n? Because if you're taking the median, then you'll have, in this case, exactly, tomorrow I'll have new markers, I'll have n½ many elements. When I'll split them, I'll have n/4, n/8, n/16, and in log n many steps, log to the base 2 and many steps, I'm done. So if it's so good, why I'm bringing it as a bad example, it's because to find the median, how do I find the median? If I just need to do it really quickly, probably I'll call sorting algorithm and take the median elements, which is chicken and an egg. So I'm calling sorting to solve sorting. So not a very good idea. First element, why do I badmouth it? Because if your array is already sorted, I think that you all know it, if my array is already sorted, then my running time will be omega of n squared will be my running time. We'll see today what is this omega thing. It means it takes no less than n squared many operations to sort the array. If it's already sorted, then you're picking the first element. So if this is bad and this is bad, what do we suggest instead? Well, let's take a random, but now let's be careful, not a random value. I'm not picking a random value because I have no idea how elements in the array are distributed. What do I pick? I'll pick a random element from the array. Maybe it will be the first, maybe it will be the second, maybe it will be the last, each one with the same probability, and that will actually work most likely very well. Picking a random value is bad, picking a random element is good. and it will probably, and we'll see more clearly what this probably means, probably will do very well. Can I improve upon it even better? Yes. We'll talk about the 5 random elements method that will say pick not 1 random element, but 5 random elements and pick their median, and this will be really good approximation of the real median. We'll talk about it much more, but yeah, sure.
How would you know like the range of your elements?
So I don't know the range. I just pick. Thanks for asking. What I'm doing is I'll say K will be, let's say that I'm using, depending on the language. In some languages, one with no parameters gives me a number between 0 and 1. I'll take this value, I'll multiply it by n, the number of elements, and I'll take the floor of it. So now I'm getting an index between 1 and n. Actually, if it's a floor, then between 0 and n minus 1. And I'll say the pivot will be A, the array, at the point, which point? The value of k that I just get. This will be x. This is what I'll use.
So you just generate random numbers until you land.
I generate random, no, I generate, if rand returns a value between 0 and 1, depending on the language, if rand is a value between 0 and 1, then I'm sure that rand times n will be a random float, non-integer, between, if it's between 0 and n, takes the floor of it, then it will be between an integer between 0 and n minus 1. And that's for sure is a legit index in the array. Now, if I want to pick 5 of them, then I'll just do it 5 times. I will not be too worried about maybe I hit the same element twice. I don't care. Make sense? So it's much simpler algorithm, and then quicksort is extremely likely to run very, very fast. We'll analyze it more clearly. More examples of randomness? Yep.
And the traveling salesman, there's the method to solve this annealing.
Simulated annealing. You are right, yes. That in optimization problem where, or you might have heard it about MCMC, or how to escape from holes, right, of local minimum. Randomness is definitely there. Yeah, that's another example where randomness saves you. So data structure, have you seen randomness in data structure?
Oh, skip list.
Skip list that we'll also revisit. Another one, very important one. Hashing. Hashing, you will pick usually some value and use it. For example, one of the common methods for hashing, when I need to ask where do I take key, k usually will be a key in my value. I'll take k, if it's a number, multiplied by a, some constant, and take the floor out of it, for example, or make it a legit index in some hashing table. But how do I pick this a? I'll try to take a random value, random float, and they do much better than trying to design what is the best constant that I can pick. So again, randomness is a huge blessing. Okay. So it's just a warning slash introduction that we will see quite a few randomized algorithms in this course. We hopefully refresh your memory for most of you. What is the definition of big O of a function? When can I say that the running time of an algorithm is order of n squared, or when is the running time is order of n cubed, or order of n log n. And I'm going to sound very obnoxious. The answer is that it's like a legal agreement between my lawyer and your lawyer, and all I'm trying to say is that my algorithm is not doing horrendously bad, but I'm not claiming that it's doing necessarily very good. All I want to say that if I claim that the running time of my algorithm is order of n squared, then it means that I can pick a value n0, some threshold of how large is the input. What are the set of inputs that I care for? Small inputs, I don't care at all. No matter what you run for small input, your algorithm will run very fast. If your input is large enough, larger than n0, and it's up to you to decide what is this n0, for any input that is larger than n0, you also, or your lawyer should show me this constant C1, such that for any input which is larger than n0, you have more than n0 many elements, up to you to tell me what is n0. You want 100, that's fine. You want 1,000, that's fine. But you have to then make your mind at some point. What is this n0? For any input larger than this, the running time of your algorithm is not larger than g of n. Your running time, your algorithm is maybe not very fast, but at least it's not terribly slow. It's not slower, it's bounded from above by this graph of g of n. You're saying t of n is order of n squared, then look at the graph of n squared. The running time of your, or the running time of your algorithm could not be more than n squared, but wait, you have still one way out. N squared times this constant. What is this constant here? Let's see, one. Maybe you measure the time by seconds. Maybe you measure the time by clicks of your clock. Maybe you measure it by weeks. I don't care. Your CPU is faster than my CPU. I don't care. Still, I claim that my algorithm asymptotically is faster. How can I show it? Because for some constant, my algorithm is faster than yours. Yours runs in n cubed, my runs in n squared, which means that no matter how, even if my computer is much slower than yours, there is some input that is large enough that my code, my computer runs fast, will solve the problem faster than yours. N squared will always beat n cubed. Maybe in some theoretical way. Maybe you need n which is larger than the number of particles in the universe. But it's theory. But there is, if you are saying my algorithm runs in order n squared, it means I can show you, if you ask, I can show you what are these two constants, n0 and c1, such that the running time is not more than c1 times n squared. That's asymptotical analysis. Okay. By the way, till when are we are done at 11, sorry. Yeah, sure, no problem. Just asking. So you want to convince your boss that your algorithm is not very slow, then you need to show your algorithm never runs in more than n squared time, provided that the input is large enough. Okay, so maybe it's slower than other algorithm, but not more than n squared, or not more than log n, not more than n log n, and so on. Now we are in the opposite position. Now your competitor submitted his or her algorithm, and you want to say my algorithm is my competitor algorithm is slow. How do you prove that it's slow? You want to show that there is once again this bound n0 and this bound c1, such that for every large enough input, every n that is larger than this n0, the running time of my competitor runs, the T of n, the running time of my competitor, runs in at least G of n, but it's G of n, whatever you want. Maybe it's 2 over n, say. Maybe it's n squared, maybe it's log n, whatever you say. But to make it a legit legal statement, it needs to be that for every n that is larger than n0, the running time for my competitor is no less than the red line, no less than n squared. The running time of my competitor algorithm is no less than n squared times a constant. Okay, but here is a bit confusing part. And then you can say, if this statement is true, then you can say the running time of the competitor is no less, is omega, big omega of n squared, big omega of log n, big omega of 2 to the n. Make sense?
Sorry, this is a dumb question. What is the omega notation? What does that mean?
It's the notation of lower bound. If I want to say that it doesn't take more than this time, the algorithm is fast, it doesn't run very slow, it's at least order of n squared. That is, if I'll give you an algorithm that would, if I'll show you an algorithm, my algorithm runs in n log n time, exactly. Then I can also say that it is also true. If this is true, then it's also true that it is order of n squared. If it runs in n log n, then it also runs in order of n squared. It also runs in order of n cubed. It also runs in order of 2 to the n. These are all correct statements. Again, order means it doesn't run slower than order of n
So
squared.
I meant like the omega.
And omega, we will say exactly the opposite. It doesn't run better than 2 to the n. It doesn't run better than 2 to the n.
Oh, gotcha.
For example, theorem. Sorting n keys takes omega of n log n time. There are exceptions, even one that we discussed today about radix. Radix does it in linear time, but that's not arbitrary keys. And in general, if you don't know anything about the keys, any algorithms that you generate will run in at least n log n time. Maybe it runs in order of n, in order of n squared, maybe order of n cubed. But order just says it's a positive thing. It's not very slow. Omega is from the opposite. It runs in at least this time. You cannot solve it faster than this time. That's what omega means. Okay. So don't confuse about the order. These are all true statements. If it runs in n log n, then it also runs in n squared, order of n squared. It also runs in order of n cubed. Now, to say that this algorithm runs in order of n cubed is like to say, the old joke of you're in a balloon. It's a correct but not very informative answer. Doesn't help you very much, but at least it is legally correct. But now our lawyers says, no, now read the small letters. What do I mean by omega versus O? There is one more twist. When I'm going back to the omega, I want to say that for any input larger than n, and no matter what input this is, as long as its size is n, it might be that no matter what input it is, I'll go for all the possible inputs, it doesn't run slower than or order of n squared. On the other hand, back to the omega, how can I convince you that something runs in omega of n log n? To prove to you that every sorting algorithm takes omega of n log n, it doesn't mean that for any input, because we just said today, for every input I can always find a very friendly, for every algorithm I can find one friendly input for this particular algorithm. It means no matter how you try, I can always, me as a vicious nasty guy, find an input that will cause your algorithm to run slowly. That's what the omega. I can find one instant is only enough. I don't care about average. I don't care about expected. The worst time is at least omega of n squared. Now, why are we using omega? We use it much less than order, but omega also gives us a way to focus on what are the dominant part. If I have a set of procedures, functions, methods, one takes 3 times n cubed, one takes something n squared, something linear, constant, all of them, what is the dominant part? The dominant part here, for large enough input, the n cubed will dominate the running time. So I'll just write it omega of n cubed. And I can ignore completely that it's 3 here at the beginning. I can ignore completely all the less important terms. Because for large inputs, this will be.
So I haven't understood the purpose of adding constants in that part.
It just, a new CPU is in the market. I still want to compare algorithm. I don't want to compare exact running time. So I'll say, I can show the constant, and once you force me to clock the running time, then I will tell you what is a constant. But no matter on which, if I'm looking at this at an algorithm that runs in order of n squared, it means no matter what CPU it will run, the difference of the constant will be on one computer it will run, if I measured it in seconds, like this, which is n squared times maybe 1. And on another computer, it will run by 2 times n squared, but the asymptotic behavior is the same. It also implies that for no matter what's a constant, for some, again, possibly completely unrealistic input, the n squared will beat the n cubed. Finally, if order was just a upper bound and omega was just a lower bound, can I actually talk about an algorithm that runs in concretely in n squared, no more, no less, almost up to constant. This is big theta. Greek letter, big theta. It means I'll say that the running time is big theta of n squared if I can find a constant, yada, yada, yada. What do I want to say? That it is both omega of n squared, and if it is both order of n squared and omega of n squared. Maybe not with the same constants. I have 2 constants here in the omega. But if the running time, if we think about a merge sort, if you think about merge sort, I know that merge sort takes order of n log n. And on the other hand, look at the theorem that I just told you. Merge sort, like any other algorithm, runs in omega n log n. So merge sort is order of n log n, and also omega of n log n. Conclusion, this plus this, saying that merge sort is theta of n log n, meaning that up to constant, it's optimal. Where are you using constants? You want to say your boss pressures you to find faster algorithm, You're saying no. I already hit the lower bound, or that is possible for solving this problem. But I generated an algorithm that runs in n log n, and at the same time there are bounds that says you cannot solve it in better than n log n. My algorithm is optimal. Talking about theta means that this is actually the running time. We are not overshooting, we are not undershooting. That is actually the running time. Modulo may be playing with a constant, maybe. It's between 2n squared and 4n squared, but only in the constant. So that's big theta. Okay, we already mentioned it in the slide. If the running time is n cubed, then it's completely correct to say that the running time is n to the 3.5. So it's also true that if it's n cubed, then it's also 2 to the n. Again, it's not very informative, but it's legally correct. But if it runs in n squared, does it also true that it's running n to the 1.5? Maybe yes, maybe no, I don't know. This statement doesn't prove nor disprove that it's n to the 1.5. It just said it doesn't run in more than n squared, but maybe it runs in less. On the other hand, if I show you for some particular algorithm that it runs like a replacement sort, or even quick sort in the worst case, it runs in omega of n squared, that is its worst case is n squared, then it cannot be true that it also runs in order of n to the 1.5. N to the 1.5 means it never runs in more than n to the 1.5, which contradicts that there is some input that calls it runs in n squared. So these two guys contradict each other. Okay, now we'll start tomorrow playing with a few examples you have in the slides of that I'll just give you pieces of code and we'll play with them and see how all the functions prepare. And I